Okay, now for something a little bit different. Let's do Louisville's theorem and the fundamental theorem of algebra. Okay, section 4.53. So we're going to use Cauchy's inequality to prove something called Louisville's theorem, and then we'll use Louisville's theorem to prove the fundamental theorem of algebra. So really something foundational in this is Cauchy's integral formula, or the extended Cauchy integral formula. So from that comes Cauchy's inequality and Louisville's theorem and the fundamental theorem of algebra in this little line of argument. Okay, Louisville's theorem states that if f is an entire function that is analytic in the entire complex plane and bounded in the whole complex plane, then f is constant throughout the entire complex plane. Or in other words, there are no bounded entire functions other than constant functions. A quick little observation, I mean, these things don't happen in the real setting. Another example of a behavior of a function from the complex realm that you don't have in the real realm. Sine and cosine functions are bounded by 1 and -1, but they're differentiable everywhere. They've even got power series representations. So this is a totally different type of behavior in the complex setting. If you don't like your transcendental functions, how about a little rational function? F of x equals 1 over 1 plus x squared in the real setting. Bounded above by 1 and below by 0. It's differentiable along the whole real line. In fact, we could create power series for it as well. But rational functions, if you want to stay away from the transcendentals. So loads and loads and loads of examples of bounded functions of a real variable that aren't constant functions. Arctangent, tangent inverse function, I think, is another one. So let's take a look at the proof of this, being it's all unusual and stuff if we're biased towards the real setting, or biased towards the complex setting in favor of the real setting. All right. And as commented, this is really going to come out of Cauchy's inequality. Okay, Cauchy's inequality allowed us to put bounds on the nth derivative of an analytic function. Here we've got an entire function, f. Say it's bounded by m in modulus. So that was the hypothesis, bounded in the whole complex plane. So let m be that bound in modulus. Cauchy's inequality, as applied to the first derivative, we're going to show the first derivative is 0, and that's how we'll get that we're dealing with a constant function. Cauchy's inequality gave us bounds on nth derivatives evaluated at points. Well, we'll use this with n equals 1, and we'll have that f prime of z sub 0 is less than or equal to this bound m divided by r, where r can be anything greater than 0. It represented a modulus here, and we've got a function that's defined in the entire complex plane. So we've got a function for which z can take on any value in the complex plane. In particular, z can be large. All right, so we've got this bound holding for all r greater than 0. Well, the only way, think limit as r approaches infinity, the only way this bound can hold for all r greater than 0 is if this modulus of f prime of z equals 0. And so f prime of z itself equals 0. And when the derivative is 0, then the function's a constant, just like in the real setting. That was something I guess we encountered back in chapter 2. But yeah, we do have that familiar behavior, that derivative is 0 implies constant function. So Cauchy's inequality gives us a bound. That bound's valid for mod z equals r arbitrarily large, and so that implies that f prime of z sub 0 must be 0. Function must be constant. I mean, we could have applied this to any of the order derivatives and they would have all been 0. But hey, we know just from this that we're dealing with a constant function. Okay, so no bounded entire functions in the complex setting. We're going to prove using Louisville's theorem, and suppose it's of interest in its own right, but I'm mostly fascinated in Louisville's theorem because it allows us to prove the fundamental theorem of algebra, which states, take any complex polynomial p of z, a sub 0 plus a sub 1z plus a sub 2z squared up through a sub n z to the n. Take a sub n to be non-zero, so we can say the degree of the polynomial is n. So that's not a hypothesis, that's just a notational constraint. And let the degree be greater than or equal to 1. So we're not considering 0-degree polynomials, which would be constant polynomials. Some people would argue they're not even polynomials. In particular, the 0 polynomial may or may not be treated as a polynomial. For us, we're taking n greater than or equal to 1. So we're dealing with something at least of the form a sub 0 plus a1z. If we have degree 1, then of course you can find the 0. If we have degree 2, then you can use a quadratic equation to find the 2 zeros. If we had degree 3 or degree 4, there's algebraic formulas to find the zeros of those polynomials as well. Not true for degree 5 or larger. A topic to be explored in probably Introduction to Modern Algebra Part 2, when you look at algebraically solving polynomial equations. All right, so the claim is polynomial, degree at least 1. There is some point z sub 0 where p of z sub 0 equals 0. That is, there exists a root of such a polynomial, has at least one root, is the claim. Okay, maybe a little bit of follow-up on that. What we would see soon in the exercises is an alternative way to state that. We'll go through the proof, of course, because it's not involved, and we've got Louisville's theorem. In the exercises, it's to be shown if p of z equals 0 for a polynomial, that polynomial can be factored as p of z equals z minus z sub 0 times q of z. Q is a polynomial of degree n minus 1. So this is sometimes called a factor theorem in certain algebraic settings. Finding a 0 of a polynomial is equivalent to finding a linear factor of that polynomial. When you solve polynomial equations back in high school, you use the factor theorem. You learn how to factor, and that's how you found zeros of polynomials. So iterating that idea, we could go through and actually write p of z as a product of linear terms, z minus z1, z minus z2 through z minus z sub n, factoring out those zeros as we go, and expressing the polynomial as a product of linear terms. You might see something along these lines expressed as the fundamental theorem of algebra in some settings. It's equivalent, at least in the complex setting. We've got the factor theorem, not in all algebraic settings, but we've got it in the complex setting. Okay, so here the fundamental theorem of algebra is stated in terms of the existence of at least one zero. In fact, we see from that paragraph below, it has to have n zeros up to multiplicity. If you'll count multiple zeros appropriately, then an n-degree polynomial has n zeros. Not the case in the real setting. Consider x squared plus 1. Hey, x squared plus 1 doesn't have any real roots, but plus or minus I are the roots if you'll let me use complex numbers. Okay, and I'll make a somewhat political argument that, yeah, the fundamental theorem of algebra, really, it's not that algebraic. It's more analytic. It's more complex analytic. All right, so let's go through proof of it. It's not immediate, but break it down into little steps. It's proof by contradiction. Assume there is no z sub 0 that makes p of z 0. Suppose that p of z sub 0 is never 0, then we're going to consider the function 1 over p of z. All right, so this would be then a quotient of analytic functions. Of course, polynomials are differentiable. As long as you don't divide by 0, apparently limit 2.24.a says, as long as you don't get division by 0, a quotient of analytic functions is analytic. And we're assuming, which will lead to a contradiction, we're assuming that denominator isn't ever 0. All right then, 1 over p of z then is an analytic function throughout the entire complex plane. What we're going to do is show 1 over p of z is bounded, and that's a problem. Okay, so we're going in the next few lines for getting a bound on 1 over p of z. We're going to take p of z, treat it like this, at least for z non-zero, a0 over z to the n, a1 over z to the n minus 1 up through a sub n. If you take the z sub n and distribute it back, you get cancellation, and that will produce the polynomial. So we've written it as a product of two things. The idea is going to be I can get a bound on one of the things and, in the sense, get a bound on the other thing. And that's how we're going to produce boundedness of the polynomial. Okay, let's look at this part in parentheses. All right, when z is big, we were to take a limit as z approaches infinity, you've got all these z's in the denominator. So if we've taken up through this term, we haven't taken the constant term. But what we've got going on here is when z is large, this term is going to be small. More precisely, the limit as z approaches infinity of these terms equals 0. Yeah, the denominators get big, the quotients get little. More professionally, the limit as z approaches infinity of this summation equals 0. Okay, so you can make this quantity small as you'd like, positive in terms of modulus, by making z sufficiently large. In other words, we could take epsilon to be a sub n over 2. Let's make the quantity in parentheses and modulus that small. Not a problem. The limit is 0. So we can make that quantity smaller than this in modulus by taking z to be sufficiently large. Let sufficiently large be parameter r. So by taking r greater than 0 such that for all mod z greater than r, we get this expression to be less than epsilon. Epsilon delta definition of limit as z approaches infinity equals L in general. But what we get from that then is we can make that term less than this choice of epsilon, provided mod z is greater than r. All right, let's do some more manipulations. Let's take that, add the a sub n in, trying to recreate that 1 over p of z function, ultimately. So add the a sub n in, we can then say that the modulus of this is greater than or equal to the absolute value of the difference of the moduli of the term in parentheses and the a sub n term. I guess it's corollary 1.4.1 that tells you that. Be a corollary, no doubt, of the triangle inequality from when we first encountered moduli. And hey, I know this quantity is less than a sub n over 2. So we're taking something less than a sub n over 2 in modulus, subtracting modulus of a sub n. What you're left with is going to be at least a sub n over 2. Remember, the first term is less than a sub n over 2. When you subtract a sub n and then take absolute values, what you're going to get is a quantity that's greater than a sub n modulus of over 2. All right, so we've got this quantity greater than a sub n over 2. The good news is mod a sub n is a constant. It's fixed by whatever polynomial we have. Also a reason to have that hypothesis be that a sub n was non-zero, or else we got something trivial here and probably not useful. Now we had p sub z expressed as z to the n times this quantity in set brackets, which is what we have up here in the modulus brackets. All right, well, modulus of p of z would be the modulus of this product. That's the modulus of the stuff in set brackets times the modulus of z to the n power. And provided mod z is greater than r, we've seen that this expression is greater than a sub n over 2, modulus of. So we get an a sub n over 2 bound on that. We'll carry the z sub n along for the ride. Oh, and we've assumed mod z is greater than r. That's where we got that bound on that first expression. So taking mod z greater than r, we get an additional inequality of the form mod p of z is greater than a sub n r to the n over 2. Remember, we're trying to show something's bounded. We're getting there. Okay, this is a lower bound on the modulus of p of z. We're trying to get a bound on 1 over p of z, modulus of. Okay, well, we might be onto something here, because we take a reciprocal of this side that reverses the inequality and gives us a reciprocal over here. In particular, it's going to give us an upper bound on the modulus of 1 over p of z. So that's where we're going, and that's why we've found lower bound on p of z itself. So taking reciprocals, we get 1 over p of z, modulus of, is less than 2 over mod a sub n r to the n. That was, whoops, that's a reciprocal. Here it is, a reciprocal of what we had here, mod a sub n r to the n over 2. Take a reciprocal, reverse the inequality, 2 over mod a sub n r to the n. And this is valid for mod z greater than r. Okay. 1 over p of z, hey, it's a polynomial. It's a rational function with a denominator non-zero. So we've got a continuous function, 1 over p of z. Only thing that could go wrong is division by 0, and we've assumed, which is not true ultimately, it's where we get the contradiction, we've assumed the denominator is never 0. Okay, then you got a quotient of continuous functions. A quotient of continuous functions is continuous. All right, so let's take a modulus of 1 over p of z. We want to show that thing is bounded. Mod 1 over p of z is bounded by, say, m. If we look at the closed and bounded set, mod z less than or equal to r. So we've taken a little disk, mod z less than or equal to r. R might be big, but still it's a closed disk. We get a continuous function on a closed and bounded disk that has a maximum. So says Theorem 2.18.3. If you do more analysis, senior level analysis, you'd show that a continuous function on a compact set has a maximum. And this is a special case of that. If you like, I probably should just quote Theorem 2.18.3. But we do get a bound on that disk, which makes sense. A continuous function on a closed and bounded disk, that's going to have a maximum. You call such a result the extreme value theorem in Calculus 1 when you're dealing with closed and bounded intervals in the real setting. All right, so we've got a bound for mod z less than or equal to r of m. I don't care what it is, just the fact that we have such a bound. And we've got a bound on 1 over p of z, modulus of this thing here, provided mod z is greater than r. So mod z less than or equal to r, one bound. Mod z greater than r, another bound. So we've got 1 over p of z modulus of less than or equal to this bound when mod z is greater than r is established here, and this bound, whatever it is, for mod z less than or equal to r. So we've got this function, 1 over p of z, bounded in modulus. It's an entire function. Certainly, assuming it's never 0, we've got ourselves a differentiable function. Quotient rule tells you how to find the derivative, valid in the entire complex plane. Then we found a bounded entire function, but Louisville says there are no bounded entire functions other than constant functions. Well, that's a contradiction, because we were given that we have a polynomial of degree at least 1, so it's got z's in it. It's at least of the form a sub 0 plus a1 z to the first power, and that ain't a constant function. So there's the contradiction. The assumption we made was that p of z was non-zero throughout the complex plane. That must be false. That's where the contradiction came from. In other words, there must be some zero, z sub 0, of polynomial p. So polynomials have zeros. Polynomials with complex coefficients have complex zeros. Doesn't work in the real setting because I need those complex zeros. Even in the real setting, even if we had real coefficients, of course, we potentially still need complex zeros. Okay, we commented about factoring. A bit more commentary, so I like this stuff, about why this is called a fundamental theorem of algebra. How do you prove it in algebra? Well, it depends on which algebra class you take. If you take senior level algebra, you prove it the way we just did. You prove it using Louisville's theorem, which is messed up because you don't have all that complex background. Why? In that senior level algebra class, I love that senior level algebra class, but why in Introduction to Modern Algebra, they go through Louisville's theorem to prove the fundamental theorem of algebra? Well, they do it because it's so hard to do algebraically. One might expect there's an algebraic proof, you know, a proof based on nothing but group theory, ring theory, and field theory stuff. And when you hear algebra, modern algebra, you think groups, rings, and fields, related structures. And it is the fundamental theorem of algebra, so you'd expect to prove it in algebra. Not going to happen algebraically in a senior level algebra class. In fact, a little reference for you here, there are no purely algebraic proofs of the fundamental theorem of algebra. I just gave you a purely complex analytic proof of the fundamental theorem of algebra. There ain't any purely algebraic proofs. I turn you loose on some of my other notes for some discussions about why that's the case. But in some sense, algebra deals with finite processes. There is no, this is misleading, there is no infinity, there's no infinite number of binary operations in a group. You can't do infinity stuff unless you can measure distances or at least have a topology. Infinity stuff requires limit stuff, and limit stuff requires either at least a topology or, more to your experience, a metric. You need a way to measure distances. And that ain't part of the structures of groups, rings, and fields. Now, there are some of these structures that do have metrics on them, but with purely algebraic approach, you can't really deal with the infinity stuff. I'm not claiming that there aren't algebraists that deal with infinity in some setting, but groups, rings, and fields, you can't take infinite sums in a field. Can't take series in a field unless you can talk about limits, because series are limits. They're limits of finite sums. You can take all the finite sums you want. Limit doesn't make sense unless you can talk about, forgive me on this a little bit, getting close to, you know, epsilon delta type stuff, more appropriately. In the graduate class, we do give a proof of it that's mostly algebraic, but it still borrows a couple of results from analysis. In graduate level algebra, modern algebra 1, we have to assume that positive real number has a square root. We have to assume an odd degree polynomial has a real zero. An odd degree real polynomial has a zero. How do you know positive real numbers have square roots? You know it because of, well, here it says right here, the axiom of completeness. The way you define the existence of square roots of positive real numbers in the real setting ultimately is related to the axiom of completeness. So it's this continuity idea. The axiom of completeness gives you a continuum in some sense. And that's beyond the realm of algebra, my kind of political stand on why there's not an algebraic proof of the fundamental theorem of algebra. But it's the axiom of completeness that guarantees you can take square roots of real numbers. How do you know an odd degree real polynomial has a real zero? Well, duh, you do that in calculus 1. You got an odd degree polynomial. If we get far away from zero, it's positive on one side and it's negative on the other side. I don't know which it is. It depends on the leading coefficients, maybe. But, well, if it's positive on one side and negative on the other, it's got to be 0 somewhere in between. So says the intermediate value theorem. But the intermediate value theorem is ultimately based on a continuum idea and based on the axiom of completeness as well. So if you'll take a graduate level algebra class, here's a link to my notes on the fundamental theorem of algebra that we go through in the graduate algebra class. Even there, you have to borrow these two results from analysis. One could argue, well, if you're going to borrow stuff from analysis, why not borrow Louisville's theorem and problem solved? But the proof explored in that algebra class is largely algebraic. And I always say, not the personal algebra folks, but without a little bit of this analysis stuff, you don't even know what the real numbers are. Without some kind of explanation of the real numbers as a continuum. And that's what the axiom of completeness gives. You can't even discuss the real numbers or the complex numbers for that matter. So in an informal sense, that's why there ain't a purely algebraic proof of the fundamental theorem of algebra, in my opinion. Yeah, if you'll take our modern algebra, Introduction to Modern Algebra 2, actually here's a link to the notes there. They go through this Louisville's theorem stuff. It's in the Fraley book, John Fraley's book that we use in modern algebra. At least I use in modern algebra. Love Fraley's linear algebra book as well. These books are dated, the linear algebra books from the 1990s. This abstract algebra book's 2003. But in there, they'll go through and give a proof of the fundamental theorem of algebra using Louisville's theorem. I've thrown some commentary in my notes in the past along the lines of, well, geez, it seems you ought to call it Louisville's corollary because it's a piece of cake if you have Louisville's theorem. The fundamental theorem of algebra arguably is not very algebraic. It's a cute little behavior given by our knowledge of analytic functions in complex analysis. Yeah, it's all a matter of the continuums. There's a little more commentary on that. I've got a number of handouts, some of them mostly historical and not so mathy, about how numbers developed and the history of the theory of equations. I mean, why ain't algebra about the quadratic equation? Why you do all this group theory stuff in algebra? Well, it turns out it's related to a theory of equation stuff. And somewhat to the fundamental theorem of algebra. Maybe one final comment about this fundamental theorem of algebra. We claimed there existed a 0 of this polynomial, and we showed there exists a 0 of that polynomial. Now, we didn't find it. In the olden days, talking 1500s and earlier, an idea of claiming the existence of something was most frequently dealt with by actually finding the thing. If you want the zeros of a second degree polynomial, you got it. Quadratic equation gives them to you. What if we got a third degree polynomial? There's an algebraic formula, as I mentioned a while ago. What if you have a fourth degree polynomial? There's an algebraic formula that gives you those 4 roots of that polynomial. You find them. Beyond that, there's not algebraic formulas. Degree 5, it's called the unsolvability of the quintic. Degree 5 polynomials and larger, there's not an algebraic formula to give the roots. Not saying there's not any formula, saying there's not an algebraic formula. See my algebra notes for details on that. But hey, we claimed the thing existed, and we showed by contradiction that it must exist. We didn't find it. In a sense, this is somewhat an indirect proof. It's not a constructive proof. In discrete math, you do a lot of constructive proofs where you claim something exists and you prove it exists because you build one of the things. It's a common approach in graph theory, in combinatorics, for example. But we claimed it existed, some z sub 0, where p equals 0, didn't find it, but we showed that it has to be out there somewhere. Existence, at least, is a step in the right direction. We'll leave it to somebody else to actually find or approximate numerically is a common thing to do. Knowing they exist is a good thing to have in your pocket before you go looking for some numerical solutions. Knowing the existence of such things is certainly necessary. So there's a neat result, I think, based on our knowledge of analytic functions. Louisville's theorem, probably not going to use it much in the future. Oh, we had to do this. This ties together a lot of the senior level classes. Hey, there's algebra here, arguably. There's a pile of analysis here because we've got these steps that work backwards. Louisville's theorem, extended Cauchy's formula, which is used to prove Cauchy's inequality. So these complex results, along with the prerequisites for those, is what allowed us to get to proof of the fundamental theorem of algebra. Geez, if I look at the big picture, it ain't that elementary a proof because it requires all this background knowledge. It's an elementary proof if you'll give me Louisville's theorem. That's Fraley's angle on it in his book. All right, so from here, it's on to the maximum modulus theorem and some applications of that. I'll see you in section 54.